this better? Yeah.
Great. Well, thank you, everyone, for being here at 10 a.m. on a Monday morning in the rain. It is my wonderful pleasure to introduce Sivan, who's going to talk today about some work on wildlife tracking. So what I find most sort of compelling and exciting about this work is back when the field of sensor networks, Internet of Things was starting, I think, circa 1999 or so, this was one of the showcase applications, this idea that tiny computing devices that could sense and communicate wirelessly would allow sort of an inspection and a data gathering of the physical world that before this was impossible, and it would lead to a real revolution in science. In fact, one of the earliest sensor networks people tried to build was something called ZebraNet, which involved like big collars on zebras with solar panels, and there were some cool algorithms, and when they tried to deploy it, it turned out that all the zebras went and smashed the collars against trees. And so we also learned about all of the physical issues. But it sort of painted this vision of being able to instrument animals at a very fine scale, and from that learn all kinds of new things for ecology, animal behavior, et cetera. And so now let's wind forward, in this 19 years. And now that vision has really become a reality. You can see just how the technology has progressed, and now the kinds of scientific innovations and the kinds of new scientific instruments we have. And so, without further ado.
Okay, thanks. Okay, thanks, Phil. So I'll talk about Atlas, a reverse GPS system that we built to track wildlife at high throughput. I'm from computer science in Tel Aviv. What you see on this map in the is tracks of 77 barn owls over one night. There are about 1 million localizations here connected with lines. About 1 every 3 seconds for every barn owl. The number is not random. It's basically all the barn owls. So the ecologists tagged basically all the barn owls in this area. This is about 12 or 15 kilometers across and about 10 kilometers. This is north, south, west, and east. They tracked basically all the barn owls in order to understand the dynamics of the entire population, as opposed to just studying a few birds. And that tracking went on not for one night, but for every night. So it was 24/7 for a few months during the nesting season. So that's one example of what this system can do. Here's another example. These are small bats, insect-eating bats. They captured them one day in a cave around here, and then track them for a couple of nights. You can see the tag, the tracking device on the back of this bat. This is about close to 30 kilometers north to south. And these are even more challenging bats. These are 7-gram bats. I mean, they didn't have a picture, so this picture is from Wikipedia, but the species is correct. They've never been tracked before because they're too light for GPS devices. And so on. And you can see some tracks. They try to understand they do have eyes, but they're apparently nearly blind, and they wanted to understand how they navigate over large distances as opposed to finding prey and so on, which they do using sonar. The tracking is done using reverse GPS principle, time of arrival localization, emitter localization, using radio transmissions, RF transmissions. So you put a radio transmitter on an animal. It transmits from an unknown location that you want to estimate XY at times that you don't really know. Even if you know when they're transmitting, you may know this up to maybe milliseconds or microseconds. But in order to localize, you need to know the transmission time up to nanoseconds. So that's really an unknown. The transmissions are being received by base stations, receivers at fixed locations that you know, X1, Y1. The receivers estimate the arrival time, so base station 1 estimates the arrival time at T1, base station 2 at T2, and so on. They send the data to a server, and the server runs an optimization algorithm to estimate XY, which is what you care about, and also T. It's part of the T is part of the equation. You throw it out, but it's there. Okay, so I'll explain more about how the localization is done. I just want to give a big picture first. So we deployed the first system, and we did all the experiments on this first system in the Hula Valley in northern Israel. There was a reason for this, and the reason is that it's a wildlife-rich area. It has lots and lots of wildlife, so there are multiple studies you can do. You need it's good to deploy these systems in areas that are really interesting in terms of wildlife because there is infrastructure to deploy. Once you've deployed them, you want to run multiple studies, not just one study. As you can see here, so Israel is here. And basically all the birds that migrate from northern Europe and northern Russia, Siberia, to eastern Africa pass through Israel. A few of them passed over the coastline. Most of them passed over the Syrian African rift, and this valley is part of that rift. It's the last green area. It's the last. It used to be a wetland. It's still used for agriculture. There are some ponds, so it's still used very heavily as a stopover boat on the way south. Once they leave here, 100 kilometers down south starts a desert of a few, I guess, 1,000 kilometers or something like this. So they need to fuel up, and when they come back, they also stop over. Many of them stop over for a few weeks and stay there. So it was an area that had potential to really use this system. This shows the tagging a year ago in spring 2017. We didn't reproduce this graph. By that time, the ecology deployed about 700 tags. Now it's more than 1,000. 24 species, mostly birds and bats. 3 or 4 species of three bats. The rest are birds. What I want to point out here is that this shows the number per family, and what you can see is that the largest number is on passerines. These are small songbirds like house sparrows and so on that are very difficult to track using other techniques because they're very light. The next bar is owls, which can be easily tracked using GPS devices, and then bats, which are not easy to track, and other birds in smaller numbers. This shows the sort of high throughput aspect. The green bars are the number of localizations per day, and they reach up to 2.5 million localizations per day. The orange line is the cumulative number. A year ago, we reached close to 500 million localizations. This reference line is the total number of localizations in a community database called MoveBank that stores not all, but a lot of the GPS wildlife tracking of different groups in the world. And it's shown as a flat line, but they also went through some significant growth. What it shows is this one system like this can produce an amount of data that's on the same order of magnitude as all the GPS tracking that's done together. I mean, not everybody puts their data on MoveBank, so it's not the same amount, but it's the same order of magnitude. So maybe the total amount is maybe produced is maybe 10 times more than MoveBank stores. We've deployed also the system in other places. So the Hula Valley system was the first system. We've since deployed it in three other places in collaboration with local groups. The first one to deploy was NIOS. It's an Institute of Sea Research in the Netherlands, in Exeter, University of Exeter, a research farm near Exeter. These two were deployed and became operational last summer. BioMove is a research effort in Germany. They deployed the system but didn't really tag any animals. It's still being deployed, and we are collaborating with the group in Australia to try to deploy there. They're trying to raise funding for this right now. So here are pictures from these other deployments. This is the Netherlands. It's deployed in a place called the Waddenzee. You can see them deploy a base station at high tide. They come with these Zodiacs, deploy them on construction scaffolding. There is no power, so you can see the solar panels. At low tide, it becomes a mud flat, and then there are birds that feed off the mud flat. And you can see here, this is a snapshot of real-time tracking. The base stations are the round circles here, so they're around. They're all around an island. You can see tracks of birds flying in and out and feeding around here. And you can see also as this is about 15 kilometers. You can see that the system, even though it's localized here, can keep tracking the birds as they fly out, but it becomes more noisy both because the signals become weaker and also the angles that the hyperbolas intersect become more acute. So that's completely normal. This is in the UK. They're trying to. It's a research farm that studies pheasants, or at least the group we are collaborating study pheasants. And you can see that there they deploy the base stations on wind turbines, very high antennas. it's a, before I move on, I want to say it's a very large collaboration. There were many people participated in this. The labs that lead this effort are my lab in Tel Aviv and Ran Natan's lab in the Hebrew University. He's an ecologist. There were other people in Tel Aviv, Tony Weiss from electrical engineering, many students, engineers from the Hebrew University, many people associated with Ran's lab, also some other ecologists in Israel, in Haifa, in Tel Chai, and also, like you see in these other groups in Europe. Two people I want to single out. This is Ran Natan with one of these barn owls, and this is Yotam Orhan. He's his lab manager, and he's really responsible for deploying all of these base stations, producing the tags, a huge amount of technical work to make this work. So it's a system, in terms of the overall project, it's obviously an interdisciplinary project. There is CS and E on one side, the technology on one side, ecology on the other side. Now, we started in 2012, reflecting back. You can ask whether did we really need to do this as a close collaboration? I think the answer is yes. There are other techniques. You can develop technology and then deliver it to scientists. I don't think it would work this way here. It's science focused. So even I decided early on that I'm going to measure this in terms of the science that's being produced, not in terms of the computer science that's being produced. I think it's really a prerequisite for collaborating with ecologists. So if you say, okay, once you produce the computer science results or the engineering results, you publish the paper, you're done, they can continue to play with the technology, they're going to abandon it. So you need to invest many more efforts in order to produce science results. Another thing that's going to come up in the second part of the talk, that it's highly multifaceted. In order to make something work, you need to resolve all kinds of problems. Some of them are research problems, some of them are just boring engineering problems, but you do need to resolve them. So I'm going to mention some of them and say a few words about the more interesting ones. Localization algorithms, this is interesting. Localization systems, embedded systems that operate in fairly extreme environments on the back of wild animals. And like we also had bats chewing off antennas and so on. So for example, the material of the antenna turns out to be very important for some species. RF technology, DSP, some of it is mundane, some of it is extreme. Visualization, analysis, you need to deliver data, you need to store the data, you need to configure and monitor these systems. So there are many aspects that you need to pay attention to. Okay, I want to move to a short video that was produced. It's kind of interesting because it was produced not by me, but by one of the ecologists. So it really shows how they view this side, multi-charter. It shows programming and preparing tags. It shows capturing wild birds and tagging them. How does the tagging work? Visualization, system monitoring. We'll see also homing in, finding trackers that fell off birds using direction of arrival manual techniques. Some of the infrastructure and so on. Let me move on to. Okay, there's. Okay, so this is a real-time view, but in season with many birds. There are maybe 50 or 100 birds, not 100, maybe 50 birds here. The movement is not really birds moving, but it's noise. It's localization noise, but you can see tracks of really birds moving. This is configuration. Here they're building, assembling the tags, soldering batteries. You can see all of the batteries over there, weighing them. This is kind of typical with the batteries. 4 grams, 10 grams. Here they're being tested, I think. Preparing, they're encapsulated and they're preparing the harnesses for barn owls. These are these backpacks or harnesses. Here this is an early attempt to glue on a barn owl. We'll see later that they put harnesses. This is one of the base stations. This is a base station in the Hula Valley where we didn't have power. Most of the places we do have power. This is homing in, trying to localize to find tags. Okay, found it. This guy's like Indiana. To me, it looks like Indiana Jones. I mean, that's my experience of him. Here, they're putting a harness on a barn owl. This is Moti, I think, the guy who made the video. These videos were taken, so you can see the tag on her back. That's a female with a tag. And you can see her feeding the chicks, and you'll see her mating in a second. And these videos were made to try to assess the impact on the birds. They basically show that there is little impact because they keep feeding the chicks, they keep mating and so on, so they're mating. That has no meaning, really. Different kind of owl. That's tagging fruit eating bats. These are tags on songbirds. That's how they put them on birds. They just glue them with surgical glue. Okay, I think that's enough. That's a large rodent. Okay, can move back to the video. Okay, before I move to the technology, I want to say a few more words about explaining again the implications for ecologists. So there are two important implications. One is the range of animals that you can study, and the second is the throughput. How much data do you get? So this is a histogram of bird species, the number of species per weight, and you can see that most bird species are around 50 grams or so. So if the technology uses 0.9 gram tags, then you look at this histogram and you can see that we can we can track 80% of bird species. So there are some bird species for which you need even lighter weight tags because they're 0.1 or 1 gram, 0.9 or 1 gram tags are too heavy, but 80% are okay. You can study them. If you go to GPS tags, GPS tags start at about 3 grams. 3 gram would be a logger. You also need to retrieve the logger at the end. The number drops to half the number of species. If you go to GPS tags that transmit the data out through satellites or through other means, they start at 7.5 grams. Again, you halve the number of species. So really the most important thing for them initially was to have lightweight tags. That generates capability that's missing in other technologies.
I assume most of the mass is basically the battery, right?
It depends. At 0.9, most of the mass is not the battery once you move to 2-3 gram. I mean, you'll see this in a second. The boards now are less than 0.5. They're about 0.3. But you'll see that in a second. The other thing is the throughput. The throughput depends both on the number of localizations per gram and also on the cost, on how much you're going to invest in order to get the data. This shows the number of the cost for different number of tags. So if you deploy Atlas, then there is a significant cost in the receivers. So even if before you tagged even one animal, you spend $30,000, around $30,000. But then the tags themselves, they cost $20, $30. So even if you deploy 500 or 1,000 of them, you're still in the $40,000, $50,000 range. If you use GPS tags, the loggers cost about 300. There are two different loggers here, and a tag that transmit the data out to satellite. The loggers cost about 300, 350 each. The tags that transmit the data out cost about $1,000 each. So the cost, tagging a few birds or a few animals is inexpensive with GPS. But if you want to tag large numbers, it becomes really maybe $200,000. Maybe ecologists can still afford this. $500,000, probably not for most studies. And it's not only the cost, it's also the number of localizations that you get out of each tag. So if it's the number of localizations is what you want, not the number of tags. Atlas produces about 1 million localizations, transmits about a million times per gram of battery. So if the tags are 2, 3 grams and up, then most of the weight is battery, and they transmit about 1 million times per gram of tag weight. If you go to 1 gram batteries, then it's about 100,000 because most of the weight is in the coating, in the glue in the coating. You look at conventional GPS loggers, GPS loggers that use conventional GPSs that actually compute the location on the bird. That's about only 200 locations per gram of battery. And if you look at tags that transmit the data out, it will be about 10. Vesper and Robin are GPS tags produced by a different ecology lab in Tel Aviv, Yossi Yovel's lab. They're baseband recording tags. They record the RF signals from the satellite, and then the localizations are produced later. So they're somewhere in between. They're not widely used, but they're somewhere in between. And if you put these two together and you look at the number of localizations per dollar or localization attempts per dollar, again, Atlas is orders of magnitude better than GPS tags. And again, these GPS offline loggers are somewhere in the middle. But they're between conventional GPS loggers and Atlas, there are many orders of magnitude in the number of localizations per research dollar that ecologists invest. So that's Atlas. It's a system I'll show later. It produces sort of GPS quality localizations. The localizations are uploaded to the internet in real time. Maybe real time is not that important to ecologists, but having them, the ability not to have the localization without retrieving the tags is very important. The tags are lightweight. This is all now, they're 0.7. They can produce tags that are about 0.7. The electronics of the tag cost about $20, and once you put in the time of the technician to assemble, it rises to something like 35, and they produce about 1 million localization attempts per gram. That's why we entitled this high throughput animal tracking. There are also downsides. The most important downsides